Good morning. We will start the module on the robot dynamics and control today. This is lecture number 1 of that module, and this is a recap of the previous thing, what you have covered so far in the class. First you started with the robot anatomy, then you saw their actuators, sensors and controllers, then how to specify the task of the robot. If you are given a specific task, how to convert that in a mathematical form. Then you studied some little bit about robot analysis, basically DH notations, kinematic analysis, forward and inverse kinematics. Then we saw a little bit about motion planning and obstacle avoidance. And then last module was on robot vision, where you saw something on image processing, some segmentation algorithms and things like that. Now today we'll start with the robot dynamics and control. Okay, in today's class what we are going to see is what is robot dynamics and control, why it is important to study the robot dynamics and control, and then what are the fundamentals of dynamics we'll study first, and then we'll move on to some application examples. So that is what we are going to cover in the today's class. Okay, so let us think of this example of 2R manipulator. You have here, these are the two links, link number 1 and 2. These are the two links of the manipulator. This is a revolute joint and this is another revolute joint. So this is 2R manipulator. So revolute joint corresponds to this R. And then you have one motor, a bigger motor, which is moving this link, and a smaller motor which is moving this link. And then at the end there is an end effector. Now let us say we have a task that we want the manipulator to move point P from PS to PF. Okay, so we are not really bothered about what is the path taken to go from point PS to PF, but we just want the final position PF to be reached. So this is a task number 1 we will consider. Then we will consider some other task also, and then I'll demonstrate why you need to really worry about this robot dynamics and control. Okay, so we want these tasks to be performed. Okay, so like just think about what all steps you will follow to achieve this task. Okay, any guesses? Could you see what all steps you will follow based on your inverse kinematic analysis? Okay, so you will find that the first step that you will follow is to find out the desired joint angles corresponding to these points PF and PS. Okay, by using your inverse kinematic analysis. Okay, you have studied the rotation matrices and how to do this position analysis. So you do the inverse analysis and then find out this angles. Now like in this case, like your theta 1 and theta 2 in this position, they will correspond to theta 1 and theta 2 at the start, and then you see here for this final position corresponding to this position, you will find theta 1 F and theta 2 F, which are corresponding to this position, and then so these are the equations, I mean these are the angles corresponding to the initial and the final position. Okay, and then you will command your motors to move the joints, okay, to go simultaneously from starting point to final point, not bothered about the path that you will follow. You see that? Now there are some of the questions. What is meant by really this command? What I wrote as a command. What is meant by command? Okay, so this can be like some kind of a voltage given to the motor or some kind of a torque given to the motor, but what is a torque? What algorithms you will follow to really apply this torque? okay, then how much I should have this torque, like what are the ranges, what is the value, okay, what all it depends upon. Okay, what if you want to take this point P from the starting point to the final point in a faster way? Okay, so naturally you will see that we need to have more torque if we want to move faster, right? Okay, so we see that like if we specify this faster movement, then because of the dynamic effects, like we have some torques to be overcome, and because of that, like you need more torques to be applied to the motor or more voltages to be given to the motor. So in general the power requirement will be higher. Okay, now after reaching the final position, how do we make sure that the links stay there, they will not move again from that final position? Okay, so these are all the questions that will be answered by the study of dynamics and control. Okay, so as you see here, there are two parts, one is dynamics and other is control. Okay, so now let us consider another example. This is again the 2R manipulator, but now the task specified is different. Okay, let us say we have to move manipulator from PS to PF in a straight line. So you understand the difference between the previous task and this task. So we want to move this in a straight line fashion as you can see on the screen. Okay, so that is a desired trajectory we want to follow. Okay, so in the previous task we are not bothered whether it goes along this straight line or it goes along any other curve. We just wanted it to move from one point to another point. Okay, in this case we want it to go in a straight line fashion. Okay, so now again you can think about what are the steps that you will follow to achieve these tasks now. What are the differences in the previous and these tasks? So what you will do typically is you will find the desired theta in terms of time, okay, theta 1 and theta 2 as a desired time trajectory. So they are functions of time here. You can see they are functions of time. Okay, and then again you will command your motors to move the joints simultaneously to follow the desired position trajectory now. Okay, in the previous case you are not bothered about the trajectory, you are not bothered about the time, like what time theta 1 should be this value and theta 2 should be this value. Okay, so here you will have a trajectory to follow. So this problem is different from the previous problem. Okay, and again here you can ask the same questions. What is meant by command, and then how much should be the motor torque, what should be the motor torque to take it from the position, starting position to final position in a straight line fashion, and then what if we want to take to this position faster, like we want to move along this straight line trajectory in a faster way, how much deviation from the straight line will occur. Okay, these are some of the questions that you will ask. Now how much will be this deviation will depend upon so many factors. One of them will be really your control algorithm. Okay, what control algorithm you will use, but you can appreciate that to again like find out what control you have to apply in this case, or what torques you have to apply in this case. You will have to study dynamics and control. Okay, so you have to study dynamics and control to get desired performance, desired tasks to be performed by your robot in a nice fashion. Okay, so now let us get into some fundamentals. Okay, so in general, so with this example we can see that all robot tasks can be finally converted in terms of either point to point movement of the joints, which is called a regulation problem, or a trajectory tracking problem. Now think of any application that comes in your mind. Say your robot is needed for the painting purpose. Okay, you have to paint some car or something. Okay, so on the surface it should move from one point to another point. Okay, and then like depending upon the motion trajectory of the spray or a spray nozzle, you have to have some joint angles evaluated, and then you have to command the motor joints to move along those desired trajectories, right? So again that problem is converted into a trajectory tracking problem. So any task whatsoever you imagine for a robot to perform, it has to finally get converted into in terms of some joint commands. Okay, either a desired trajectory tracking type of a problem or a regulation problem. Okay, so you have to move either from one point to another point in a like in a fashion not bothered about the trajectory. Okay, and in the other case you have to move from the same point or like some different point to follow a particular trajectory. Okay, so these are the two important classes of the problems you will come across in the robot manipulator. So any task which is specified for the robot will get finally converted into one of these two kinds of a problem. Okay, do you see that? Okay, now to get the appropriate torque inputs to achieve these regulation and tracking tasks, we first need to understand what is dynamics. Okay, and next we need to develop control laws or control algorithms. Okay, these are some kind of algorithms which will specify your torque values in terms of whatever sensor feedback you are getting. Okay, and you have to use understanding of the dynamics to develop these control laws. So next we will move to understanding what is dynamics. Okay, so we will consider again the same example, 2-hour manipulator. Okay, in this case you can see that there are this torque 1, tau 1 over here and torque tau 2 over here. This torque is supplied by the motor. Okay, now a question that we ask is, given the forces and torques, can we find out the joint angle history? Okay, or in this particular case, given this tau 1 and tau 2, this tau 1 and tau 2, can you find out angle theta 1 and theta 2? Now to do that, we need to have the differential equations of the motion for this manipulator system. So the whole idea is to get these equations of motion. So now we'll move from the what we want in the actual robot to how it is represented mathematically. So we have to represent motor dynamic, the robot dynamics. We have to represent the robot dynamics in a mathematical way. So how do we do that? There are two fundamental approaches to doing that. One is formulation using Lagrange equation, and other is Newton's method. Okay, you are familiar with this Newton's method, right? You all studied so far in your curriculum this Newton's method. Now what we'll go in the details of formulation using Lagrange formulation in the next couple of slides, and then Newton's method, I'll just give you steps how do we approach to get these equations of motion using Newton's method for a particular case. Okay, so we'll study the Lagrange formulation in detail. Now for that, first thing, this method is based on the energy. Next, the equations in this method are obtained without considering the internal forces. This is a very important point for the Lagrange formulation. All the forces or reaction forces, they are neglected in this case. You don't have to worry about them. See, in the Newton's method, you had to do first the free body diagram, and then you consider this balance of the forces by Newton's method, and then you are obtaining the equations of motion. But in Lagrange formulation, we don't bother about the internal forces or the reaction forces. Next is, this method is ideal for more complex robotic manipulator configurations. Okay, you imagine how if you have to apply for a 3D complex robot manipulator the Newton's method, there are many forces that you have to imagine, and you have to get your force free body diagrams correct. But in the Lagrange formulation, you avoid all those complications. Okay, suppose other example is like, say if you have a flexible manipulator, there are flexibilities in the manipulator, and then you want to find out the equations of motion. In that case, it becomes very easy to get the equations of motion based on the Lagrange formulation. Okay, and Newton's method application becomes very tough for flexible manipulator kind of a problems. Now, so in general, this method is better than Newton's method for robotic applications. Next, we will see what is this method. Okay, what do we do in the Euler-Lagrange equation? So this is a basic form of the equation. You can see it is d by dt of dou L by dou q dot minus dou L by dou q minus tau y. Now here L is Lagrangian, L is Lagrangian, and it is given by kinetic energy minus potential energy. So Ke and P are basically kinetic energy and potential energies. And this tau I that you see in the equation is the external force in the direction of generalized coordinate Qi. So Qi is a generalized coordinate. So typically Qi will correspond to the number of degrees of your robotic manipulator. Okay. So if you have, say, 2-link manipulator, you'll have 2 Qi's. Typically there will be theta 1 and theta 2 for our manipulator that we are seeing the example of. Next, we'll take some example and apply this Lagrange formulation to the example problems, and then see the beauty of how you get the equations of dynamics. Okay, so you can see here the system kinetic energy is given by this half mx dot square for the simple spring mass system. Then potential energy is given by half kx square, this term here. The Lagrangian L will be given by this kinetic energy minus potential energy, and your Lagrange equation we can see now d by dt of dou L by dou q dot. Now q dot in this case is x dot, so you differentiate this partially with respect to x dot, and then you will get this mx dot here. So d by dt of mx dot minus, you differentiate this term again, because see L is not, see you see that you are taking here dou L by dou x, and you are potential energy is only dependent on x. Okay, kinetic energy is independent of x. So you will take only this term in your this part of the equation, which is dou L by dou x. Okay, so you get this kx, and that is equal to F, which is a force applied in the direction of x. Okay, so that is the way you write this Lagrange equation, and you simplify like by taking this derivative, and you will find that your standard spring mass equation is obtained. So you have not drawn free body diagram in this case. You have not considered any forces, force balance, etc. Directly from the energies you have got the final equations. Okay, so this is a way you will get the equations for the robot manipulator also. Now let us consider a second example. We have another robotic manipulator, but a single link manipulator. You can see here that we have this single link connected to the motor through a gearbox now. Okay, so in general theta m and theta L, they are different. So theta m, maybe for this particular theta L you get larger theta m. Okay, so there is a gear reduction in between. So that gear reduction ratio is n is to 1. So can you write down now the expressions for this kinetic energy? You can see that kinetic energy of this manipulator is half Jm theta dot m square plus half Jl theta dot L square. Okay, now you need to see that there is only one generalized coordinate. You may choose it either theta L or theta m, because they are both dependent on each other. Okay, so you need to express theta L or theta m in terms of other variable, and then you should use it for the equations. Okay, so that is very important point to note. Like your theta m in this case is a generalized coordinate we have considered. So theta L needs to be expressed in terms of theta m. Okay, so by doing that you get this equation. So now half Jm plus Jl over n square theta dot m square. So theta dot m is your generalized coordinate. Okay, now potential energy is the next term. So you will get potential energy by mg into L into 1 minus cosine theta L. Okay, so now let us use our Lagrange equation. First form this Lagrangian L is equal to kinetic energy minus potential energy, and then you apply your Lagrangian equation, which is this equation. Okay, and by applying this equation you will get these terms now. So you see that when I take derivative of L with respect to theta m dot, partial derivative dou L by dou theta m dot, I will get contribution from this term, and that when differentiated with time I will get this term. Okay, now next contribution is dou L by dou theta m. Okay, so if I differentiate this L with respect to theta m partially, this term will not contribute anything, and this term will contribute this part. Okay, this is how you get the equation. And then tau is a now external force. We can have tau consisting of motor input u and the damping torque. So we can see now what we have as tau. So this tau has u part, and then this is a damping part. So these are the damping coefficients Bm and Bl on load, on motor side and the load side. And then you have to take this divided by n square, because it is Bl into theta dot L is a damping term. Okay. So you will get in general this equation for tau. Now the second part, you see that there is n square term here. Bl into theta L is a torque. Okay. So where is this second term coming from? Is basically when you transfer that torque to the motor side, you have to again divide by another L. Okay. Because of that you get this n square term. You all understand that? Okay. So in general, your equation then can be written as this. So you have j times theta m double dot plus b times theta m dot plus this capital C times sine of theta L, which is theta m over n, that is equal to u. Now j here is the inertia which is transferred to the motor side. Okay. So you can see this Jm plus Jl over n square term. Okay. And B is the damping which is transferred to the motor side. Okay. So you will get Bm plus Bl over n square term over here. And then this C, capital C, is given by this gravity force term. Okay. Now let us again come to our basic equation, Lagrange formulation. Okay. Now what we want to do is to extend this understanding to so that we are able to apply it to our robot manipulator. Okay. We want to use this understanding for application to our robot manipulator. Okay. So for that, you just imagine what you need for applying this technique to the robot manipulator. So first thing is how to find out the kinetic energy of your robot. Okay. So what is the general formula for the kinetic energy? So you see now that the total kinetic energy of a robot link will be given by this formula. For that matter, this is valid for any rigid body. Okay, any rigid body in space will have this formula for kinetic energy. So it consists of two parts, you can see. The first part is because of the translation, and then the second part is because of the rotation. Now this translation part has this Vc term. So this Vc is nothing but the velocity of Cg of the body or the robot link. So this Vc is vector is given here. So all these bold quantities, you understand that they are vector quantities. Okay. So this is our familiar half mv square kind of a term, which is generalized for the rigid body case. Okay. Now what is the rotational part? The rotational part consists of half I omega kind of a term, but in this case you will observe that your I, which is inertia matrix, is in general given by all these elements. Okay. So you have these diagonal entries for inertia of the rigid body about the axis of the coordinate frame, and then these are the cross coupling terms. Okay, and then this omega is a vector of the angular velocity of this rigid body or the rigid link of a robot. Okay, now this kinetic energy can further be expressed as this part. You have kinetic energy is q dot transpose dq q dot. Now this q's are generalized coordinates. So you see here that we have expressed these velocities of the CG of robot links or rigid body in terms of the generalized coordinates. Okay, and then this D matrix has all the terms corresponding to the translational part and the rotational part also. So this will be in general the expression for kinetic energy of a robot link, and then the total energy you will find it as a summation of all these kinetic energies. Now this can further be written in terms of the elements of this D matrix as Dij times q dot I q dot j. So you see that this is a quadratic form, q dot transpose dq q dot. This D is in general n by n matrix, okay, for all n links of the robot or for all n generalized coordinates of the robot, and then this is expression which is expanded form of the expression for this quadratic form. Okay, so you can see that the D matrix is symmetric in nature. In general, you will have for the robot manipulators that you are talking about, this D matrix will be always a positive symmetric definite, positive definite symmetric matrix. So this D is positive definite symmetric matrix, and this quadratic form can be expanded as half Dij. They will in general depend upon q and q dot I q dot j. Okay, so next we will see how we can manipulate these terms so as to get now a Lagrange general Lagrange equation. Okay, so we want to use now Lagrange equation with this form of a D or this form of a kinetic energy. So how do we do that? So let us see. Now we will construct first our Lagrangian. L is equal to Ke minus P. So I have substituted here for my kinetic energy the term that I obtained in the previous equation. You can see the same term over here, and then Pe is a potential energy which will in general depend upon Q. Okay, it is not dependent upon the Q dots. Okay, so it is only a function of your generalized coordinates, not their derivatives. Now from there you will get now dou L by dou Q dot. If you differentiate this L with respect to Q dot, you will find that it can be expressed as this value. Do you see that? So only one Q dot is remaining here, other Q dot is gone now because of the derivatives. Next you have to take d by dt of dou L by dou Q dot. So you take this derivative and you will find that you get this term. Now you observe that this is a product of two terms, Q dot and dkj. Okay, so you have to apply this derivative of products, and then you will get first term as q double dot j times dkj. Okay, and the second term you have to again apply d by dt to dkj and multiply it with q dot j. Now you can see that I can simplify these further. This term remains as it is, the first term will remain as it is. The second term I can differentiate first partially with respect to qi and then dqi by dt, which is qi dot. So you get this as summation of, now this will appear as a summation over I also. Because there are many number of coordinates. Okay, so you'll have to in general carry out summation over I from I going to 1 from 1 to n. Okay, so this is dou dkj over dou qi, okay, multiplied by qi dot, that is this d by dt of kij term. So this is a first term in the Lagrange equation. Okay, now the second term, which is dou L by dou qk, will be simplified as these. Again we use the same thing here, and then we get this equation. So you can see from the previous form of the kinetic energy, when we differentiate partially with respect to q I, we get this part here. Okay, and this part is our potential energy contribution. Okay, so our total equation, now taking both the parts together, can be written in this form. Okay, we have just taken the first part, which is this. It's up to this point, the first part, and then it is added with the second part, which is basically this term combined with this term. Okay, you see this simplification, how we have done that. We have just combined the terms involving qi dot and qi dot and qj dot. We have combined the terms containing qi dot and qj dot together in this single term from both the parts, and we have formed this equation. Now we will interchange the order of summation and use the symmetry of this D matrix. Okay, and then from there we will get this part, like the first part, which is del dkj over del qi multiplied with qi dot and qj dot, can be split into these two terms by using the symmetry of the matrices. The matrix T is a symmetric matrix, so I have this kj and ki splitting here, and then I will take a derivative with respect to qi and qj here, and then I will get this final term. Now the next term, so this total term summation of this part that can be written now as summation of these three parts. Okay, summation over ij, and because we have simplified the first term in this fashion, we get this summation, total summation as this. Okay, do you see what is happening? Next, we'll get the final equations in this fashion. So you get here the contribution in terms of acceleration terms. So these acceleration terms, you can see they are all basically because of the parts in the kinetic energy expression. Okay, dij were the parts in the kinetic energy expression. So there are the elements of the kinetic energy matrix D. Okay, you remember how we expressed our kinetic energy? It was basically half q dot transpose D times q dot. Okay, and then this D matrix has this dij terms which are appearing in the acceleration as a terms to multiply the acceleration of generalized coordinates. Okay, so you see in this equation the term dkj multiplied by acceleration term is directly gotten from your kinetic energy. So you see that once you get your kinetic energy, you can directly write this first term. Okay, see now what we are like aiming at is writing this equation directly without considering these differentiations in the Lagrangian formulation. Okay, so to do that, first part of your equation you can directly see is coming from the kinetic energy contribution terms. Okay, basically this dij matrix or dkj in this case. Okay, now the next term can be expressed as this summation. Okay, we have basically separated out q dot I, q dot j terms and multiplied by some c elements, and these c elements we have just derived and they are expressed to be of this form. Okay, so in the previous slide we had seen that your c elements are of this form. So the final equations of your manipulator are obtained in this form. Okay, so you have this standard form of the equations of the manipulator: dq q double dot plus cq q dot. C will in general depend upon both q and q dot, but not q double dot. Okay, times q dot plus g times q, which is a gravity vector, that will be equal to tau. Now let us see what is the physical meaning of each of these terms. These d terms are basically inertia terms. Okay, and this is a inertia because of the translational acceleration q double dot. Okay, then your centrifugal acceleration terms and centripetal acceleration terms or centrifugal acceleration terms and Coriolis terms they are combined in this term C. Okay, the term C Q Q dot, the term C Q Q dot, and then your gravity vector is in this G term. Okay, and that will be equal to your external forces. Now these external forces can be torque applied by the motor, or it can be damping torque also. Okay. Another thing to notice here is that your C terms are dependent only on D matrix. Okay. So once you know your D matrix, you can use this formula to get your C terms. Okay. So it all boils down only to finding what is the kinetic energy and potential energy, and then by directly using this formula you can find out the different parts of the Lagrange equation or equation of the dynamics of your manipulator. Okay. So you don't have to carry out all this differentiation every time. Okay, you can carry out, like you can just find out this D matrix for your energies and then use that in this form to get the final expression for the equation. So that reduces your tasks a lot. Okay. So now what it matters is to finding the kinetic energy and potential energy of the system that we are talking about. So let us now see some example. Again, our 2-hour manipulator example. We apply these concepts and then find out the equations of motion of this manipulator. So for this manipulator, you can see that the kinetic energy, you have studied the Jacobian in the previous classes. So we can make use of Jacobian to finding out the velocity of CG of these links. So velocity of CG for the first link will be given by this Jacobian times the Q dot vector, and then this velocity is again Jacobian of that link times Q dot is the velocity vector. Okay, and these Jacobians are given with these expressions. Okay, now you can see that now velocity C1, which is this CG of link 1, will be given as minus L C1 sin Q1 into Q1 dot. Okay, if I expand this in terms of a vector, in terms of its components, and then the y component of the velocity will be L C1 cosine Q1 into Q1 dot. So the velocity has, you know that the velocity of this link CG is in this direction, and it will have in general x and y components. So y component is coming out to be positive and the x component is coming out to be negative. You can see here. Okay, like that you can like analyze this expression and break down into the different velocity components that are constructing the velocity of link 2. Okay, so you will get these velocities first. To find out now kinetic energy, you make use of these velocities. So you will find now this is the expression for translational part of the kinetic energy based on the velocity expressions that we have seen in the previous case. So in the general fashion, you can write this velocity as Jacobian transpose multiplied by Jacobian into mass, and then this is m2 again multiplied with the Jacobian transpose and Jacobian, and then this matrix will be the part of a D matrix contributed by the translational energy. Okay, now how about the rotational part of the energy? Yeah, we'll see that the rotational part we have to find out from the omegas. So what is omega 1? Omega 1 is q1 dot and omega 2 is q1 dot plus q2 dot. Okay, so rotational kinetic energy will be half I1 into omega 1 square plus half I2 into omega 2 square, and you plug in these values for omega 1 and omega 2, and you will get this expression for rotational kinetic energy. We have expressed it in the same form as a previous form, which is q1 dot transpose multiplied by some matrix into q1 dot. Okay, so that way it will be very easy to now identify the terms in the D matrix. Okay, by taking summation of this part and this part in the translational case. So you sum up these two and you will get your D matrix. Okay. Now potential energy of a system is given by this expression. This you can find out by seeing where are the locations of Cg and then multiplying by corresponding mass and gravity term. So height of Cg with respect to your reference you take for first mass and the second mass, and then you will get this final expression for potential energy of the system. Now using the previous formulation that we have seen, we get these expressions for D1, D11, D12 and D22. You notice that D12 is equal to D21, and then these elements of this matrix C, they are obtained in this fashion by using our previous formulation. So these are all the elements of C, and combine this thing together, next you will get the equation, final dynamic equation of the motion for the 2D robotic manipulator or 2R robotic manipulator. Okay. Now next we will see some properties of these in the next class. So let us first see, if you want to go for the Newton's method, how we'll go about. Okay, these are the steps that you will follow to apply this Newton's method. First you will carry out kinematic analysis of the robot, then you will find out the accelerations by differentiating your velocity terms to find out accelerations. Okay, these accelerations then you will use for like finding the inertia forces, like inertial forces, and then draw free body diagrams for your manipulator, and then you apply Newton's laws, which is sigma fx, sigma fy, sigma fz direction, all three directions you apply the Newton's laws. Sigma fx is equal to mx double dot and all those things you know, and then you will apply this Newton's laws for moment also, like moment direction also, and then you find out the equations of motion. So you can also write down directly in the vector form these equations of motion. So instead of drawing the free body diagrams, you can just consider the vector form, and then you can write down directly in the vector form the equations of motion, and all the signs and all those things will be taken care of in the vector form. Now for robotic manipulator, this 2R manipulator, you will again carry out we will follow essentially the same steps. Okay, you will first carry out the kinematic analysis as we have seen, and then you will find out accelerations of the CGs of the links. Then you will draw free body diagram. In this case it is easy to draw the free body diagram in this case, and then you will apply Newton's laws to find out finally the expressions of the equations of motion. Okay. Now you will find that these equations of motion you obtain from the Newton's formulation and Lagrangian formulation, they will be exactly the same. Okay. So now we will use this understanding to basically generate our equations of motion for the robotic manipulators. Okay. So this is a way how the dynamic equations of motion for the robotic manipulator are obtained. Okay. So we will stop here, and in the next class we will continue with this robot dynamics. We will see how to extend this in general for the N-link robotic manipulator, and then we will have some introduction to the control in the next class. Okay. Thank you.